Okay, so review question 15 on exam 1. It's a calorimetry problem. So we're placing a 825 gram iron block, it's heated at 352 degrees, and placed in an insulated container, and that should be of negligible heat capacity, containing 40 grams of water at 20 degrees. What's the equilibrium temperature of the system? If your answer is 100 degrees, determine the amount of water vaporized. So I'll just add a couple of diagrams here that might be helpful when sort of considering the problem. So we can sort of show the evolution of the system. So we're putting a pretty large block, almost a kilogram of iron, into a very small amount of water, only 40 grams of water. So sort of maybe a small amount of water here, and there's a iron block, a large iron block at a very high temperature. Okay. This is the iron block initially at 352 degrees. We're going to ignore, there's no information about the air in the container, just ignore any changes in the air temperature, assume it to be evacuated. And then we got this water at 20 degrees. So you've got two different systems. Let's zoom in here so you can see this. So you got two systems at different temperatures, so that means thermal energy will be transferred from the system at a higher temperature to the system at the lower temperature. So heat's going to flow out of the iron and into the water, and that will cause the water's temperature to increase and cause the iron block's temperature to decrease. Now, what we have to figure out in a sense is that we're not going to change the phase of the iron block, but we may end up changing the phase of the water. So the first thing the water can do is heat up from 20 degrees to 100 degrees. There's a couple of ways you can figure out that number using our calorimetry equations. So I just want to figure out how much energy does the water require to heat up from 20 degrees to 100 degrees. So Q water equals M water C water delta T. So I'm going to draw this sort of small because there's going to be a lot of work on this page. So this is going to be a 0.04 kgs, 4190 joules per kilogram Kelvin, and it's a change of 80 degrees Celsius, which is the same as a change of 80 degrees Kelvin. So I think this works out to be around 13,400. So the Q water to go from 20 to 80 is 13,000, and I'll keep some extra figures here. I won't round until the end. Okay. Now you can ask yourself two questions here. You could ask, in a sense, you could consider that if that energy were to flow out of the iron, how much would the iron's temperature change by? Or you could think, in a sense, assuming that the final temperature is 100 degrees and no steam has been formed, and compare the two numbers. And I'll do both just for the purpose of the review. So if we were to make the assumption that the iron cools down from 352 to 100, well, its Q in that case will be again the mass of the iron, C of the iron, times delta T. So in this case we've got 0.825 kgs. 448 is the specific heat capacity, and we can assume that to be constant over this temperature. That could probably be more explicitly stated in the question. And then this would be negative 252. So the energy that would have to flow out of the iron to get it to 100 degrees would be 93,000 negative 139. So you can see that the energy, in order to get the iron block down to 100 degrees, would take a large amount of energy to be removed from the iron block. And to get the water only up to 100. Oh, sorry, excuse me, I see this mistake now. This is 20 to 100. Sorry, I just had 80 in my mind from the difference. Only requires 13,408. So there's definitely going to be some steam formed. We can now conclude that the final state will have at least some steam. So just again to do the separate sort of further review case, if I wanted to think about during this first stage, what we have is that 13,408 joules will flow out of the iron block and into the water. So if we were to remove the 13,408 joules from the iron block, let's figure out what that delta T would be. So the delta T for the iron block after the first stage, taking out in the process of heating the water up from 20 to 100. We've got, again, this is not completely necessary to solve the problem, this is just for additional review. Divided by the MC of the iron, so 448 joules per kilogram Kelvin, and that gives me a temperature change of about 36 degrees, negative 36 Kelvin, which is the same for delta negative 36 degrees. So in heating the water up to 100 degrees, the iron block's only going to cool down by 36. So if this is stage sort of 1 of our process, that's what would stage sort of beginning of stage 2 look like. So now what we would have in this particular case is we would have the water at 100 degrees. Iron block having cooled down by 36. So the iron block will be at around about 316, and the water would be at 100 degrees. So this is sort of our stage 2. Stage 2. So we can still see that the iron block is still significantly at a higher temperature than the water, and so our energy is going to continue to flow out of the block into the water, but as soon as you add energy to water that's already all at 100 degrees, it then has to go through a phase change. So let's figure out how much energy would be required to change all of the water to steam. So the next calculation. So think of our Q for the water for the steam formation. If we were to do all of the water, so that would be the mass of the water times latent heat of vaporization, which would be the 0.04 kgs times the latent heat of vaporization, which is a very large number. It takes a lot of energy to convert water from a liquid state to the gaseous state. So this number works out to be 90,400 joules. Okay. So in a sense that if we look at this particular number now and think about the overall numbers, so originally what would happen is that in cooling the block down from 352 to 316, it would give up around 13,500 joules. If it wants to cool all the way down to 100, it would give up 93,000. So if you take this much, this 13,400 from this much, you end up with roughly 80,000 joules. Could come out of the block and still have the block at 100 degrees. Now to convert all of the water to steam takes 9,400. So there's not enough energy. Not enough energy can be removed from the block to convert all of the water to steam. But we're going to get pretty close to converting almost all of the 40 grams, but not all of it. There will be some liquid water remaining at 100. There will be some steam at 100, and the iron block will be at 100. So if we want to figure out what is the mass of, so if we've answered sort of the first question, we did the equilibrium temperature of the system is 100 degrees, and if your answer is 100, determine the amount of water vaporized. That's our final process. So now we know that the final state's 100. So if we wanted to think overall, I'll try to fit this in here, just again show you some extra numbers. So the Q of the iron plus the Q of the water equals 0. And I'll try to zoom in here, our final calculation. So I know the Q of the iron it goes the mass of the iron, C of the iron, its final temperature is now going to be 100, minus its initial temperature 352. I'll drop out the units here just for give myself more room. But again, the delta in Celsius is the same as the delta in Kelvin. The water goes through two different stages. First, have to heat up the mass of the water, the seawater. Its final, in the liquid state, is 100. Its initial temperature is 20, plus the mass of the water times the latent heat of vaporization, all equals 0. Now, what we do know is that this number, to get the iron block from 352 down to 100, that's this number up here. This is our negative 93,139 joules. To get the water up from 20 to 100, we've already calculated that number up here, the 13,408. So that's where we're sort of saying that we have about 80,000 joules left for creating steam. So if you bring this one across, this will become a plus. Take this one away, it will be a minus. So the amount of energy that can come out of the iron block to create steam is booked out to be 731 joules. So to find the mass, you just divide that number by the latent heat of vaporization, and the mass of the water as steam or vaporized is 0.035 kgs, which is almost all of the water, which is 35 grams. So because we have, to convert all of the water to steam is 90,000. We have almost 80,000 joules to remove from the iron block. We convert almost all of the water to steam. But the final stage is definitely 100. The final temperature is definitely 100, and with 35 grams of steam. So to draw this last picture. What the final system would look like. So now we'd have barely any water left in the container and the calorimeter. So we'd have our iron block instead of 100 degrees. Our water down here, the 5 grams that's remaining, is at 100 degrees, and then the sort of water vapor is also at 100 degrees, and that would be the equilibrium state of the system. So, final, that's the whole question. So again, you figure how much energy it takes the block to cool down to 100, how much energy it takes the water to heat up to 100. See that there's a huge difference between these two numbers. So we know that we're definitely going to create some steam. To figure out how much steam, or if maybe convert all of the steam, we then have to compare how much additional energy will be required to for the water to convert all to steam. And once you subtract the 13 from the 93, that number is not as big as that. So we can't convert all of the water to steam. Then we figure out what the difference is to figure out how much steam is formed, and then we have our final state of the system.